A pleasant election day to everyone. We are the Group 1 and we will be discussing the different pharmaceutical aids and necessities. First off, let me read to you our objectives. At the end of the lesson, the student should be able to identify the different pharmaceutical aids and necessities. Second is to describe the properties of different pharmaceutical aids. And lastly is to discuss the importance and application of pharmaceutical aids and necessities to pharmaceutical preparation. So, what is pharmaceutical aids and necessities? First off, let's first define pharmaceutical aids. Pharmaceutical aids are drugs or substances that have no or have less therapeutically value or pharmaceutical effects. Many times, pharmaceutical aids are referred to as pharmaceutical necessities because it is essential on formulating chemicals or substances such as tablets, injections, ointment, solutions, and food to have a palatable effects in substance and is essential to our daily needs. Pharmaceutical aids are important agent to preparations, preservative, and storing of pharmaceutical products. Example of preparation that have pharmaceutical aids are the preparation of hygiene products, cosmetic products, and also the preparation of foods, such as flavoring and coloring. It is also an agent for preservative that is used for antibacterial, antimicrobial, and disinfectant. Just for example of preservatives are salt, propanoic acid as preservative for food such as cheese, baked goods, or additives for artificial fruit flavors, and benzoic acid that is used as antimicrobial preservatives in food and beverage such as carbonated beverages. Lastly, pharmaceutical aids are also an important agent in storing pharmaceutical products such as antioxidants, as it helps to prevent the early decay of products. Example of an inorganic antioxidant that is used in storing pharmaceutical products are sulfur dioxide, sodium bisulfate, and nitrogen. Sulfur dioxide is known to protect types of dispensing containers such as bottle glass as it have a chemical form that possesses antimicrobial action. Sodium bisulfate is also used on delaying oxidation of a active substances of a product. And lastly, nitrogen is used in storing pharmaceutical products as it have a effect that delay the process of molecules to break down. Pharmaceutical aids are classified in different uses such as an acid and bases, a buffer, an antioxidant, in uses in water, in glass, pharma- and pharmaceutical aids that have no therapeutically value like nylon, bombs, and many invention of humans that have no therapeutical effect that have pharmaceutical aids. And lastly, for making a dosage forms like tablets, capsules, and powdered, and many more. In the next preceding slide, we will give example of different classification of pharmaceutical aids and necessities.
And now I will discuss one of the major subjects of pharmaceutical aids and necessities, which are the acids and the bases. Acid and base are used for the conversions of drug to chemical form or the salt form convenient to their product formulation. So we will discuss first the official inorganic acids, starting with the boric acid, NF26 or National Formulary 26. It is also known as boracic acid, hydrogen borate or alto-boric acid, and agua boricada. We have also the native or the natural boric acid, which is called the sasolite. Boric acid is usually found in seawater, plants, and mostly in all fruits and in volcanic steam jets. It has a weak acid nature that only salts produced by the replacement of one proton per molecule and can be obtained in aqueous solution. It is soluble in water and alcohol and freely soluble in glycerin, boiling water, and boiling alcohol. However, with the addition of hydrochloric acid, it decreases its solubility in the water. It is not absorbed by the skin unless the skin is broken. Boric acid largest material source is the combined form, which are the following. First, the rasonite or kernite. Second, the borax. Third, the boracalcite. Fourth, the colemanite, and lastly, the tincal or the native borax. Boric acid also comes in three forms. First, the colorless, odorless, and pearly scales. Second, the six-scaled triclinic crystals. And lastly, the white odorless powder, which is unctuous to touch or soapy feels. The scale and the crystalline forms are more suitable for the aqueous solution since powder floats on top of water. Boric acid has a pharmaceutical use of antiseptic because of its weak bacteriostatic, which means the agent that prevents the growth of bacteria. Also, it is an eye wash to ease mild cases of irritated eyes and buffer in ophthalmic solutions. However, the toxicity of the boric acid makes it unfit to be taken orally. So the commercial products of boric acid are the insecticides, fungicides, herbicides, and antiseptic for minor cuts or burns. The second official inorganic acid is the hydrochloric acid National Formulary 26, with the other names of muriatic acid, spirit of sea salt, marine acid, and spirito di salmarina. It is an aqueous solution of hydrogen chloride gas of not less than 35% and not more than 38% weight of hydrochloric acid. The hydrochloric acid has a properties of colorless fuming liquid and has a pungent odor. Nevertheless, a non-fuming solution can be prepared by diluting with 2 volumes of water. It is more highly ionized than most other strong acids and attacks many metals with evolution of hydrogen. However, the muriatic acid is a technical grade of hydrochloric acid containing 35% to 38% hydrochloric acid and a numbers of impurities, including the chlorine, arsenous, and sulfurous acids, and iron that results to a yellow color. The hydrochloric acid is used as a pharmaceutical aid of acidifying agent, especially in the laboratory, because of the virtue of strong acid character. It reacts with organic molecules which are weakly basic to form usually water-soluble hydrochloride salts. Also, it converts normally water-insoluble organic bases into a water-soluble form for extraction or separation purposes. Since salts of most organic amines are solids, treatment of liquid organic bases with hydrochloric acid can render the composition suitable for the incorporated into a solid dosage form. We have also the diluted hydrochloric acid, a solution of hydrogen containing not less than 9.5 grams and not more than 10.5 grams of hydrochloric acid in each 100 ml of solution. It exists in the normal gastric juice about 0.2%, aiding in the conversion of pepsinogen into pepsin and proteins into peptones and gastric antiseptic. It cures gastric achlorhydria or the absence of hydrochloric acid in the stomach and hypochlorhydria, the deficiency of HCl in production of the stomach. It is usually given in the doses from 1 to 10 cc, highly diluted with water and to be supplied through a glass tube or straw avoiding solvent action with on the enamel of the teeth. They are crystalline and may be administered in capsule form. They liberate hydrochloric acid in the stomach, the glutamic acid or the betaine residue being metabolized at the same time. The commercial product are the muriatic acid. The next official inorganic acid is the nitric acid, NF26, also known as spirit of nitre, aqua fortis, and agua forte. It is an aqueous solution that produces a yellow stain on animal tissues, but it is due to the nitration of the aromatic amino acid, phenylamine, tyrosine, and tryptophan. And this reaction is also known as xanthoprotic test. Nitric acid is a highly corrosive fuming liquid, which means that can lead to an excessive damage and has a highly irritating odor that can cause irritation to the nose, throat, or lungs. Also, it has a properties of strong monoprotic acid. So, monoprotic acid are the one that can donate proton or hydrogen atom in aqueous solutions. So nitric acid can oxidize all common metals to produce the nitrate salts of the metal, however, with the exception of the gold and the platinum. It is used extensively in organic chemistry and substituted with NO2 or the nitro group to produce trinitrotoluene or TNT. It has a similar acidic properties with the hydrochloric acid. The uses of nitric acid is acidifying agent for bases, used in manufacture of sulfuric acid, coal tar dyes, and explosive. It is also a nitrate ion in the preparation of milk of bismuth and externally used to destroy cankers and warts. So some commercial examples of nitric acids are the explosives, nylon, fertilizer, and detergent. Next is the phosphoric acid NF26 with the other names of orthophosphoric acid and acido-orthophosphorico. It is a colorless, odorless, and syrupy liquid having a specific gravity of 1.71, a non-volatile, and has no oxidizing properties. It is used as an acidifying agent. It is also treated with sodium hydroxide at a particular concentration to produce HPO4 and H2PO4, and also a solvent in the preparation of anilridine injection. Some examples are fertilizer, cleaning products, and food additives. We have also the diluted phosphoric acid, which is used as a tonic and stimulant to the gastric mucous membranes, a synergistic substance to pepsin and acids to the formulation of peptones. And diluted phosphoric acid is also used in making some pharmaceutical preparations. Sulfuric acid is also one of the official inorganic acid. It is also known as oil of vitriol, vitriolic acid, and acetidivitriol. It is a colorless and odorless liquid of oily consistency. It has the properties of evaporation when strongly heated, but does not volatilize or evaporate at lower levels of heat. It has a strong diprotic acid. So diprotic acid are the amine acid with two hydrogen atoms in its molecules that are capable of being released or ionized with water. So in preparing the sulfuric acid, there is two ways, which are the lead chamber process and the contact of catalytic process. So lead chamber process is the method of producing sulfuric acid by oxidizing sulfur dioxide with moist air, using the gaseous nitrogen oxides as the catalyst. The reaction taking place primarily in a series of large box-like chambers of sheet lead. So the lead chamber process mainly used in the manufacture of fertilizer. The other way is the contact of catalytic, where sulfur dioxide and oxygen pass over a hot catalyst, unite to form sulfur trioxide, which in turn combines with water to make sulfuric acid. The catalyst used is the vanadium or the platinized silica gels. So contact of catalytic produces most of the commercial sulfuric acid today. So even though they are different ways, they are still both have the same principle, that is oxidation of the sulfur dioxide to sulfur trioxide and adding enough water to form sulfuric acid. So the sulfuric acid has a use of dehydrating agent in the preparation of pyroxylene USP26 and an oxidizing agent, sulfonating or sulfating agent. Also, because of its strong diprotic acid, it is utilized to form salts and basic organic drug molecules. So some commercial examples of sulfuric acid are the fertilizer, lead acid battery, and drain cleaner. So the last official inorganic acid is the acetic acid. It is also known as the glacial acetic acid. It is a colorless liquid with a pungent smell. So acetic acid is infinitely miscible in water and also miscible with alcohol, glycerol, ether, and carbon tetrachloride. So it is practically insoluble in carbon disulfide. So it has a pharmaceutical use of irrigation solution with some bacteriostatic properties. So the irrigation solution are any fluid used to rinse an organ or body cavity. And now, we will proceed to the official inorganic bases discussions, starting with strong ammonia solution. It is also known as ammonium hydroxide and stronger ammonia water. It has a properties of clear or colorless liquid with pungent odor. When the ammonia solution exposed into air, it loses its ammonia rapidly because it evaporates easily. It can also serve as a liquid in forming soluble complex ions with many metal cations. Here in ammonia solution, the hydroxides or the insoluble in salts become soluble in ammonia solution. In using it, we should be careful because of its hazardous distinctive. So we need to handle it with care because of its caustic nature and irritating properties of its vapors. We should cover the closure with clothing while opening to avoid direct contact with the vapor, and lastly, do not taste or inhale the vapors. It has a use of Bronsted base in many applications to form ammonium salts of acids, manufacture of nitric acid and sodium bicarbonate. It is also used in preparation of aromatic spirit and ammoniacal silver nitrate solution. We have also diluted ammonia solution, known as ammonia water or household ammonia, prepared by from strong ammonia solution with the appropriate quantity of purified water. It contains not less than 9 grams and not more than 10 grams of ammonia in each 100 ml. It is not to be used in contact with the skin and eyes. Avoid breathing ammonia vapors and use the products in a well-ventilated area. It is employed as circulatory stimulant through inhalation of vapors and externally used as a counter-irritant. Next is the calcium hydroxide United States Pharmacopoeia 32, and the other names are slake lime and calcium hydroxide. It has the property of white powder, having an alkaline bitter taste. It is slightly soluble in water, glycerin, and syrup, but very soluble in boiling water and insoluble in alcohol. It has an ability to absorb CO2 from the air, and with that, it forms calcium carbonate, giving the cloudy appearance of calcium hydroxide solution. In preparation of calcium hydroxide, it is manufactured from lime or calcium oxide through the addition of water in limited amounts or slaking. Hence, it derives the name of slake lime. The official solution of calcium hydroxide is the calcium hydroxide solution USP26 or the lime water. It is a clear, colorless liquid having an alkaline taste and is alkaline to litmus. The calcium hydroxide USP32 are used medically as fluid electrolyte and as topical astringent. It is used in pharmaceutical preparations for its potentially highly hydroxide ion concentration to react with the free fatty acids in various oils and to form calcium soaps which have emulsifying properties. Its carbon dioxide absorbing properties are useful in gas traps. It is also combined with sodium hydroxide in a mixtures as soda lime and used for its ability to absorb carbon dioxide from expired air in metabolic function tests. Slake lime or calcium hydrate is a compound used to make mortars, plasters, and cements. In dentistry, calcium hydroxide is used as a root canal filling. So, calcium hydroxide is usually found in facial cleanser, depilatories, hair color, and bleaching conditioner and facial moisturizer. Now, the potassium hydroxide national formulary 26 with the other names of caustic potash and potassa. It is a white or nearly white fused masses, small pellets, flakes, or sticks that have a crystalline fracture. It is a very delinquent so that it rapidly absorbs both moisture and carbon dioxide from the air. It has a caustic or corrosive effect on the tissues due to being a very strong base, so it needs to be handled carefully. It has the use of caustic, principally in veterinary practice in the form of chemical cremation, in order to hasten the decomposition of the tissues of dead animals, so that what is only left behind are the bones and hard tissues. It is also a saponifying agent to hydrolyze esters of fatty acids into their constituent alcohols and potassium salts. Also, widely used as aqueous and alcoholic volumetric solution for titrating acids, and it enjoys widest use as a base or alkaline agent. It is usually found in hairspray, household products such as oven and grill cleaners. It is manufacture of biodiesels and soft soaps. The next base is the sodium hydroxide, also known as caustic soda and soda lye. It occurs in a dry, hard, brittle, and white stick in a large, fused, opaque, and white stone-like masses, having a dense crystalline fracture in small pellets and other forms. It has the characteristic of easy deliquescence that rapidly absorbs moisture and carbon dioxide in air. Like potassium hydroxide, it is highly ionized in solutions, making it one of the strongest bases available. It is very soluble in alcohol, ether, and glycerin. Reacts with the salts of all metals in solution, precipitating almost all of them except those alkali metals and ammonium as the insoluble metal hydroxides. Also, sodium hydroxide is a strong base capable of damaging the tissues. In the pharmaceutical aids, it used with the same purpose of potassium hydroxide. However, it has more advantage because of its less deliquescence and probably milder and cheaper. Therefore, it is extensively used in industrial purposes. This base is usually found in biodiesel, hair moisturizer, drain cleaners, and use of caustic soda for paint scraping. We have here the sodium carbonate, also known as monohydrated sodium carbonate. It is an odorless, colorless crystal or white crystalline powder and has a strong alkaline taste. It is insoluble in alcohol. The sodium carbonate exists in three well-characterized hydrates. So the hydrates are the number of moles of water in the compound. First is the monohydrate or the Na2CO3H2O, which is only contains 1 mole of water in the compound. Second, the heptahydrate or Na2CO3 7H2O. So from the word hepta, it contains 7 moles of water. And lastly, the decahydrate or Na2CO3 10H2O. So basically, it means that it contains 10 moles of water in this compound. Sodium carbonate is made by the Solvay process. Solvay process is the saturating the cold concentration solution of sodium chloride with ammonia and then with carbon dioxide, which results the formation of sodium carbonate. In pharmaceutical preparations, it is used for its basicity in pharmaceutical preparations where it will form sodium salts of acidic drugs. Next is the soda lime USP38. It is used as a mixture of calcium hydroxide and sodium or potassium hydroxide or even both intended to use in metabolism tests, anesthesia, and oxygen therapy. It has a function of absorbing the carbon dioxide in a closed system. It will react with the carbon dioxide in the form of sodium carbonate to form calcium carbonate, thereby regenerating the sodium hydroxide. Next is the potassium bicarbonate with the other names of potassium hydrogen carbonate and potassium acid carbonate. It is a white crystalline, slightly alkaline and salty substance. It is produced by the passage of carbon dioxide through an aqueous potassium carbonate solution. It is soluble in water but insoluble in alcohols and other organic solvents. It is used as a buffering agent for pharmaceutical preparations.
So next is the buffer. So when we say buffer, we are already familiar of this, that the buffer is the chemical system that control the pH in solutions or in some pharmaceutical products within certified limits for these following reasons: for the chemical stability, solubility of the drug, and the patient's comfort. So, buffer, ginagamit ito siya, sabi nga, to control the pH or to resist the changes of pH in a chemical. Dahil there will be times, may mga instances talaga that when we store a chemical, kunwari yung chemical na yun is neutral, then we store it in a long period of time, then nag-change siya into basic because of the influence of external factors. That's why ginagamit tayo ng buffers to maintain the pH ng isang chemical na kahit anong tagal na in-store natin yung chemical na yun, hindi nagbabago yung pH niya. That's the use of the buffer. So, there are buffers that is composed of a weak acid and its salt at tinatawag siyang conjugate base. Once na weak base na naman siya, and its salt conjugate acid ang tawag sa kanya. So, the buffer, when we use buffer, it should not react with other chemicals in the preparation. Hindi dapat siya nagre-react sa chemical na ginagamit natin in the preparation. So, there are things that we need to consider when choosing a buffer. So, first, volatile species should not be used as buffers. So, like the word volatile means it quickly evaporates into gaseous substances. So, those volatile species hindi dapat ginagamit as a buffers, just like the acetones or other chemicals that is volatile. Madaling nag-evaporate. Second is, it should not have any influence on the pharmacological activity of the API. So, it should not have any influence daw on the pharmacological activity of on the API. API is the active pharmaceutical ingredient. So, yung buffer na ginagamit natin, dapat it doesn't have any influence on the pharmacological activity of the API, just like the acetaminophen contained in a pain reliever tablets. Like that kind of mga active pharmaceutical ingredients. And last, the use of pharmaceuticals should be considered in choosing a buffer for a product. If it is to be ingested, buffers containing borates should not be used as they are toxic. So there is a things talaga na kailangan natin i-consider when we choose a buffer for a product. So, if it is ingested daw, if itinitulon natin, pumapasok sa lalamunan natin, sa loob ng tiyan natin, hindi dapat tayo gumagamit ng buffer that contains borate because they are toxic systemically, just like the sodium borate. We have two inorganic buffer system. So, the first is the phosphate buffer system. So, when we use phosphate buffer system, it has its advantage where it contains dihydrogen and monohydrogen phosphate ions which are found normally in the body. But it has also its disadvantage where the insolubility of the phosphate salts of such metals such as the silver, the zinc, and the aluminum support microbial growth. So, these different metals daw na nandoon sa phosphate buffer system, it is insoluble and it support microbial growth. So, next is the borate buffer system. The borate buffer system naman, it contains metals that would precipitate in the presence of phosphate. So, they are toxic and it is suitable in external preparations, ophthalmic and nasal solutions, but is contraindicated in parenteral solutions. So, the borate buffer system, hindi siya pwedeng i-take orally na ipasok, itutulon natin dahil, sabi nga, they are toxic.
Kagaya nga nung sinabi ko kanina, and sa mga bagay na dapat natin i-consider to choose buffers. The buffers that contains borate, hindi talaga pwedeng i-ingest for it is toxic.
And it is suitable lang for external preparation, just like the ophthalmic and nasal solution. Hindi rin siya pwedeng i-inject. Sabi nga dito, it is contraindicated in parenteral solutions, like just the injections, the implantations, hindi siya pwede. Once na, dahil dangerous ang borate, just like the sodium borate, talagang hindi siya pwede i-take orally or i-inject sa ating katawan. It is suitable only for some external preparation. There are 3 primary borate buffer system. So, for the first one, the Feldman buffer system. So, the Feldman buffer system, it has the pH of 7.6 to 8.2. It is consist of boric acid and NaCl to make it isotonic and sodium borate. So when we say isotonic, it taking place with normal contraction. Para magiging isotonic siya, they added them an NaCl or the sodium chloride. The other one is the Atkins and Pantene buffer system. So the Atkins and Pantene buffer system has the pH of 7.6 to 11. Again, its pH is 7.6 to 11. It consists naman of sodium carbonate, boric acid, and NaCl. And the last one is the Gifford buffer system. Ang Gifford buffer system naman, the pH of this is 6 to 7.6. It is similar to Feldman buffer system, but NaCl is replaced by KCl to make it hypotonic. Similar lang daw siya sa Feldman buffer system, but
Pero yung NaCl or the sodium chloride, na-replace lang ng potassium chloride to make it hypotonic.
So, hypotonic naman, it's having a lower osmotic pressure. Yun ang pagkakaiba ng Feldman at ng Gifford buffer system. So, the standard buffer solution, buffer systems in pharmacy can be roughly categorized into first, the standard buffer system. The standard buffer system, it is designed to provide a solution having a specific pH for analytical purposes. The second one is the actual pharmaceutical buffers. It is designed to maintain pH limits in drug preparations. So, kung yung standard buffer system, it is provide a solution. Yung actual naman, it is designed to maintain pH limits in drug preparations. So, let's move on to antioxidants. So, when we say antioxidants, in the word antioxidants, means it inhibit oxidation, or it prevent, it resists, it hinders the oxidation. Antioxidants is a compound that function chemically as a reducing agent. So, the reducing agent, it means the redox chemical reaction that loses or donates an electron to an electron recipient. So, that is what the reducing agent is. It is also a pharmaceutical necessity. Antioxidants should be physiologically inert in pharmaceutical preparation. So, when we say antioxidant, it is a chemical compound that protects cells. Protekta siya ng cells against the effect of free radicals. The mechanism of action of antioxidants. Either the antioxidant oxidizes in place of the active constituents, or inversely, the antioxidant reduces the already oxidized active constituent back to its normal oxidation state. So, there are factors that need to be considered also in selecting a suitable antioxidant. So, first, An antioxidant in a pharmaceutical preparation should be physiologically inert. So, physiologically inert, it means it is a gas which has no toxic or anesthetic properties and does not act upon the heart or hemoglobin, or it means inactive or unreactive. Sabi dito, an antioxidant in a pharmaceutical preparation should be physiologically inert. Wala dapat siyang toxic or anesthetic properties. Next, the possible toxicity of both the reducing agent and its oxidized product must be assessed. Next, one should consider possible solubility problems between the reducing agent and the drug. So, we should consider also na may mga solubility problems, may matutunaw. When the word solubility, matutunaw siya, madidissolve siya between the reducing agent and the drug. And last is very strong reducing agent will form explosive mixtures when combined in dry form or in concentrated solution with strong oxidizing agent. So, very strong reducing agent magpo-form daw siya ng explosive mixtures once na ikinombine siya in dry form with strong oxidizing agents. So, there are different examples of antioxidants. First is the hypophosphorus acids. So, the hypophosphorus acids, the use of this is the formation of free iodine is prevented in diluted hydriodic acid and syrup. Its presence in ferrous iodide syrup ensures the non-formation of both ferric ions and molecular iodine. The salts of hypophosphorus acid are antioxidants. The sodium hypophosphite is a preservative in certain foods. It is also a preservative in certain foods. And ammonium hypophosphite is likewise a preservative in many preparations. Next is the sulfur dioxide. It has a synonym, the sulfurous anhydride, or aka sulfurous anhydride. Its uses, it will protect many susceptible compounds from oxidation by reducing oxidized forms back to their original compounds or by reacting with oxygen before the susceptible compounds do. It is usually in injectable preparations in ampules or vials. It is used in industry to bleach wood pulp, to fumigate grains, and to arrest fermentation. So, that is sulfur dioxide. So, makikita niyo naman natin sa picture, this is the sulfur dioxide. It is a colorless gas with a suffocating odor. Next is the sodium bisulfite or sodium metabisulfite, or aka ay sodium hydrogen sulfite, sodium acid sulfite, and leucogen. The uses of this is it prevents oxidation of the compounds of phenol or catechol nucleus to quinones. Bisulfite may also be found in ascorbic acid injections as a reducing agent. So, it is also found daw in ascorbic acid injections as a reducing agent. It prepares water-soluble derivatives of normally insoluble drugs. Metabisulfite is an ascorbic acid injections as reducing agent. So that is the sodium bisulfite or sodium metabisulfite. Next is the nitrogen. The use of nitrogen. As an inert atmosphere, it retards oxidation in oxidation-sensitive products and replaces air in containers for parenterals and solutions for topical applications. So, in the word retards, ang nitrogen daw is pinapahina niya or dinidelay niya ang oxidation in oxidation-sensitive products. And nire-replace ng air in containers for parenterals. Parenterals, it is injections or implantations, and solutions for topical applications. So for another antioxidant, we have the sodium thiosulfate. So the uses of this sodium thiosulfate, it contains sulfur in two different oxidation states. The oxidized sulfur atom is in a positive 6 state, resisting further oxidation, whereas the remaining sulfur atom is in a 0 oxidation state. This oxidation polarity allows the compound to act as a reducing agent. Also, sodium thiosulfate acts as an antidote for cyanide poisoning. So, ginagamit din siya, act as an antidote for cyanide poisoning. And last, an antioxidant is a sodium nitrite. Sodium nitrite naman can act as both a reducing agent and oxidizing agent. It is an antidote for cyanide poisoning also. It enhances flavor, production, and prevent microbial growth. So, same as the sodium thiosulfate, sodium nitrite is an antidote also for cyanide poisoning. It enhances flavor production and prevent microbial growth.
Now we will discuss the glass and its types. So glass is an inorganic material, mostly silicates, or mixture of materials which solidifies when heated up and then cooled without undergoing crystallization. So glass containers are among the primary packaging materials that has found use in the pharmaceutical industries. This is very important in pharmaceutical industries. So glass is the container material of choice for most small volume infusions. So these are usually the first choice of packaging materials in pharmaceutical products, and a large number of pharmaceutical formulations have been packaged using glass containers such as small volume infusions. It is formed by the silicon oxide tetrahedron. So for the composition of glass, it is principally made up of silica with varying degree of calcium oxide, sodium oxide, aluminum oxide, barium oxide, and other forms of oxides. So the high melting point of glass is due to the presence of silica. The melting point and melt viscosity of the glass is modified by the addition of oxides. So the glasses are able to be solidified and molded because of the oxides. Selecting the appropriate glass composition is critical facet of determining the overall specifications of each parenteral formulation. So next, we can see here in the table are the list of substances that will impart different colors when added to the glass. When copper 1 oxide is added, it will impart opaque red, green, or blue color. Tin 4 oxide will render opaque, calcium fluoride, milky white, manganese 4 oxide, violet, cobalt 2 oxide, blue, finely divided gold, red, purple, or blue, uranium compounds, yellow and green, iron 2 compounds, green, iron 3 compounds, yellow, chromium, green, cadmium sulfide, yellow, and lastly the selenium, which will impart red or pink color. So the European Pharmacopoeia and United States Pharmacopoeia classified different types of glass based on their hydrolytic resistance. It is also important to know that not all glass containers are good for pharmaceutical use, which is why glass are classified into types. So the factors considered when selecting glass containers are sensitivity to calcium and barium ions, thermal expansion properties, hydrolytic resistance, and limited alkalinity. This is why glass containers are categorized into different types for pharmaceutical uses. So glass containers are classified into types 1, type 2, type 3, and type 4 glass. So type 1 glass is also known as neutral. Type 1 is a borosilicate glass with good chemical resistance. It is used for pharmaceuticals requiring the least reactive containers. So this is composed of silicon dioxide and boric acid with low level of non-network forming oxide. This is a chemically resistant glass with low leachability and low thermal coefficient of expansion. So low leachability means its substances cannot be easily are removed by chemicals, and also it has high thermal shock properties. It is suitable as packaging material for most preparations, whether parenteral or non-parenteral. But usually, type 1 glass is the most preferred glass for parenterals. Uh, they can also be used to contain strong acids and alkalis because this type of glass is chemically inert and is less reactive to strong acids and alkalis. Due to its composition, neutral glass has a high hydrolytic resistance and high thermal shock resistance, which makes it suitable for most preparations. So example of typical type 1 products includes tubular glass vials, prefillable syringes, cartridges, ampules, small volume parenterals, and diagnostic reagents. So next is the type 2 glass. These are soda lime treated glass. So this type of glass is treated with sulfur to the internal surface of the glass, which reduces ion exchange, making this category suitable for solutions administered intravenously. So high proportion of sodium oxide and calcium oxide makes this glass chemically less resistant. It melts at lower temperature and renders easily to mold into various shapes. So type 2 glass has lower melting point when compared to type 1 glass, so it is easier to mold. It has higher thermal coefficient of expansion than type 1, and it has lower concentration of migratory types than type 3. It is also suitable for most acidic and neutral aqueous preparations, whether parenteral or for non-parenteral use. It is due to its high hydrolytic resistance. Example of a typical type 2 product is a molded glass infusion bottle. Next is the type 3 glass. Type 3 glass is an untreated soda lime glass. So this is still a soda lime glass but is not treated with sulfur, unlike the type 2 glass. This is the type most commonly manufactured. This is composed of high proportions of sodium oxide and calcium oxide. Type 2 glass is chemically less resistant because soda lime silica glass only has moderate hydrolytic resistance compared to the first types of glass. They melt at lower temperature and easy to mold into various shapes. And they have a lower thermal coefficient of expansion than type 1. This type of glass is also suitable principally as a container for parenterals. They are used in packaging non-aqueous preparations and powders for parenteral use, with the exemption of freeze-dried preparations. It is also used in packaging non-parenteral preparations. So the typical type 3 glass products are molded glass syrup bottles and tablet containers. Lastly, the type 4 NP or general purpose soda lime glass. So this type of glass has low hydrolytic resistance and is reactive to chemicals. This is not used for products that needs to be autoclaved, as it will increase erosion rate of the glass container. This is used to store topical products and oral dosage forms. So this type of glass is used for less reactive substances only, and mostly used for topical products like creams and other oral dosage forms of drugs. So now we will discuss the water and its pharmaceutical uses. So water is the primary solvent to most solutes due to its properties. So we all know that the water is considered as a universal solvent because more substances dissolve in water than in any other chemicals. A pure water is tasteless, odorless, and a clear liquid. Pure water is free from impurities, which is why it has these characteristics. Water is also an extremely important pharmaceutical agent. Purified water is used as an excipient in the production of non-parenteral preparations and in other pharmaceutical applications. So we have different types of waters. First one are the natural waters. Alkaline water usually contain appreciable quantities of sodium and magnesium sulfates, which makes it alkaline. Next is the carbonated waters. This is charged with carbon dioxide under pressure while in earth. chalybeate waters have iron in solution or in suspension and are characterized by a ferruginous taste. So maybe it tastes like iron. So lithia waters occurs in the form of carbonate or chloride. So lithia water is defined as a type of natural or mineral water which is characterized by the presence of lithium salts such as carbonate, chloride, or citrate of lithium. So saline waters, this is also known as purgative waters. This holds relatively large amount of magnesium and sodium sulfates with sodium chloride. Next is sulfur waters. This has hydrogen sulfide. Sulfur water is a condition where water is exposed to hydrogen sulfide gas, giving a distinct rotten egg smell. This type of water has a unpleasant smell. So lastly, the siliceous waters. This includes very small amounts of soluble alkali silicates. Next, we have the official USP waters. Most liquid injection are quite dilute, the component present in the highest proportion. Purified water USP. So these are waters that has been filtered or processed to remove impurities like chemicals and other contaminants. This is obtained by distillation and other processes. This is not used for parenteral and ophthalmic products. Next is the water for injection. These are clear, colorless, and odorless liquid purified by distillation over reverse osmosis and contain no added substances. So we learned in our previous lesson that this type of water is free from pyrogen and is used as a pharmaceutical aid, specifically used as a vehicle or solvent for the preparation of parenteral solutions. So third is the bacteriostatic water for injection. It is prepared from water for injection that is sterilized and packaged in pre-filled syringes or in vials containing not more than 30 ml. It also has one or more suitable antimicrobial agents. It is used as a sterile vehicle for parenteral preparations. It should be noted that the label should state not for use in neonates. This should not be used in neonates or newborns because it might cause gasping syndrome to them due to the toxicity of the bacteriostatic agent, which is benzyl alcohol. Next is the sterile water for injection. This is a clear, colorless, and odorless liquid for parenterals. This is sterilized with no antimicrobial agent or other added substances. This is a water for injection that is sterilized and packaged in a single dose containers of type 1 and type 2 glass. Next is the sterile water for irrigation. This is a clear, colorless, and odorless liquid, a water for injection that has been sterilized with no antimicrobial agent or other substances. So this is used as a solvent for a irrigating solution. So irrigation solutions are intended to flush and help in cleansing cavities and wounds. So this type of water is for external use only. So it should be noted that the label must say for irrigation only and not for injection. And lastly, the sterile water for inhalation. This is prepared from the water for injection, sterilized and packaged with no added antimicrobial agents. So heavy water is isotopes of hydrogen, which are deuterium and tritium. So sterile water for inhalation helps to humidify inspired gases, thus managing dryness of the respiratory mucosa. So this is usually administered for nebulization. So here ends our report, and we hope that you've learned a lot from our topic, and thank you so much for listening.